Hello and welcome back to Differential Equation section 2.4, Mechanical Vibrations. So what we're going to do here is actually take our second order constant coefficient homogeneous ordinary differential equation, right? And give it application. It's going to be an equation that explains the spring that is attached to some kind of a massive object and the way that system would behave once that system is disturbed, right? So it's not in equilibrium position. If it's in equilibrium position, the system doesn't move. So if you just hang something on a spring and leave it there, it will not do anything. But if you give it a little tug or something, it will oscillate. And the oscillation without further interventions is the one that we are looking at here. Now, you can force motion, like bring energy into the system constantly, and that's going to be non-homogeneous case that we're going to cover later, and a non-homogeneous case will have equal to cosine 2x, which means, right, you're constantly hitting on the whatever period you have on the cosine, which is that 2x, right, related to period. Or you will have delta function, right? You smack it once, or you will have something. So now we're going to observe the system, and we are going to take a look at three cases, and so on. So let's go and discuss these cases. So the equation that we want to consider later, not now, later, is going to be mx double prime plus cx prime plus kx equals this forcing term t. Now, to understand x, right, well, so x is going to be the distance between the equilibrium and the whatever the object that it's connected to the spring is. So the graphic looks like this. You have some object that is connected to the spring. Let's say this is where the equilibrium is. This is the offsets part. So this distance here is x, and it's clearly dependent on time, because at, I don't know, 1 o'clock it's there, at 2 o'clock it's there, and so on, right? So it changes. Now, what we are considering in this first step is just a homogeneous case. So we're not looking at this equation. We are actually looking at the equation mx double prime plus cx prime plus kx equal to 0. That's the homogeneous case that we want to consider. We have the good old m to be the mass of the object, right, kilograms. We have c, which is the dampening constant, and we have to talk about damped versus undamped. So dampening, and we'll talk about what that is. And then we have k, which is good old spring constant, right? So this is our equation. Now you read the problem, you pick up those numbers, you plug them in, and then use the previous section to solve it. So we are learning just one step, like one layer on top of it, where we learn which part is what. Right? So interesting. So so what do I have? We are going to have the cases where so this dampening, right, the C, if C equals to 0, we call the motion undamped. And if c is larger than 0, we have damped motion. There we go. Would not work. We'll see why. And we use equal to 0, right? In which case, as the name, free motion or whatever. That one is the our homogeneous case, so equal to 0. What else do I need? I think that's it. So now, what do we know about this? Well, if you look at the equation, you can write mr squared plus cr plus k equal to 0. And we use the I can't remember. Quadratic formula. Yes, quadratic formula. Use the quadratic formula, write a, b, c, and plug the values where they belong. So negative b, that's negative c, plus minus c squared minus 4mk divided by 2m, right? And these are your r's. And now you have these cases here where the thing under the radical is negative, 0, or positive, right? You can have those three cases. And those three cases all have physical ramifications when you have this system moving.
Which three cases?
When c squared minus 4mk is less than 0, equal to 0, larger than 0, right? You can have three cases there.
Right.
What happens in the case when it's less than 0? When you have less than 0, remember what you have as the solution. You get complex numbers. So what do you get as a solution? What kind of solution you get? Conjugate pair, which is, right, complex numbers, so conjugate pair, which is sines and cosines. So what's happening with the sines and cosines? It's going to do this forever, right? But you have to be very careful, right? You have this, mass is always positive. We don't have to look at this mass over here and consider it at all. In order for the object to exist, right, in the world, it has positive mass, right? There's no negative mass as a concept. So we don't have to consider the denominator at all. Look what happens with that c over there. All right? You have negative c in that equation. So c better be positive value because you get negative c. Negative c gives you negative e in a solution, right? E to the negative value. So now let's write the solution for this real quick. So if we have c larger than 0 and c squared minus 4mk less than 0, we have complex conjugate pair. Complex conjugate pair. That's what we have. Now, that complex conjugate pair is going to be our good old R equals A plus minus BI, which gives us the solution, right, of y equals e to the ax C1 cosine bx plus C2 sine bx. Now, I don't like these variables because we are supposed to use, now it's physics now, so t, time, is our variable. So I have to recast this as y of t, which is e to the at C1 cosine bt plus C2 sine bt. T is the independent variable, time. Now, I also said that if you carefully look at this A, what is A? Well, A is negative C over 2m, right? So A is negative C over 2m from above. And we know that 2m is always larger than 0. That's given because 2 is positive number and m, if something exists, right, it has positive mass. So we are looking for, so we see that everything depends on this C. If C is positive, this A becomes negative C over 2m. So look what you get. You get that y of t is equal to e to the negative C over 2m t, and then you have all this C1 plus cosine, whatever the hell bt, you can figure out b, plus C2 sine bt. This over here is a negative number in front of t. How do you graph exponential equation with a negative exponent? How do you graph it? Starts high and goes, it's a decay, right? So you would graph it this way. Would you agree? But there's also this part, right? Exactly. So these exponential equations are just this. Let's say you start oscillating here and it goes whee. And this is called a damped system. And this is exactly what happens, guys, when you have an object on the spring. It starts with a high amplitude, and it loses energy over time, and it loses energy over time, and then it stops. Yes?
So when C is 0, that E term becomes 1, and it never decays.
Very good. That's why it's called undamped. It is going to oscillate forever. So put that in a zero gravity environment, in vacuum, far away from galaxies, set it in motion, it will go on forever. It has to, because there's nothing to hinder it. If you hang something on the ceiling right now and let it ding all over it, right, it will eventually slow down, right, because anytime it goes up, gravity will be pulling it down, right? And when it goes down, it will be falling on its rate, but the spring is pulling up. And eventually, that system would die. You all know that system would slow. Here is your mathematical representation of that type of a motion. Every oscillation that we have on this planet is going to eventually stop because of all of the forces, right? You have friction, you have air resistance, you have, right, gravity. All of these things working together are going to, yes, you can make an awesome system, right, that it's very low right? But just wait 100 years, it will stop. All right? I mean, you know, depending on how good your design is, it will stop. Yes. Oh, yes, and that's going to be our 2.8. That's exactly what it does. So now, Evan already pointed out that if C equals to 0, which means there is no middle term, if there is no middle term in our differential equation, C equals 0, that kills E. If E dies, there is nothing to squeeze this sine cosine oscillation into 0, into stopping, so it will oscillate with the same amplitude in time forever. And that's called the undamped motion. Now also, observe what happens if C is negative. Can't be in the physical realm. Because if C is negative, minus and minus would give you plus, and then your oscillation would start at 0 and then do this, right? And yeah, but we know that if you hit an object, it cannot gain energy and feed energy into system to become unbound like that. So there are things to consider here.
But don't we have to like use that graph method for what? But it's not used at all?
Potentially, I don't know for what.
Do follow for the door stoppers at your kid and stop.
Yes. I'll figure things out, put it on a test. Some people are rolling their eyes, I see. Great. Now, there are more things to consider in this case. I am going to so let's first look at one of the calculations. This is just really quick. You guys can do this in 3 seconds. So this is problem 16. They just give you that M is 3, that C is 30, K is 63, X0 is 2, and V of 0 is 2 as well. Those are initial conditions. So let's write the differential equation. It is mx double prime plus 30x prime plus 63x equal 0. To solve this, we just use the previous section, right? We write characteristic equation. Hopefully you see that you can kick 3 out so you don't have to suffer too much. So r squared plus 10r plus 21 equals 0. And as you factor, you can divide both sides by 3. 3 just goes away. So when you factor this, you get r plus 7 and r plus 3, right? Equals 0. So one r is 7, negative 7, and the other r is negative 3. So your solution, x as a function of time, so t is the main variable, is going to be c1 e to the negative 7t plus c2 e to the negative 3t. I know. So that's your x of t, and now you need your v of t, which is x prime of t. Remember that x is a distance, right? When you differentiate distance, you get velocity. That's why they give you v0 of 2. So when you differentiate this puppy, you get negative 7 c1 e to the negative 7t minus 3 c2 e to the negative 3t. And now you can plug values in. We have 2 and 2, right? So 2 is equal to c1 plus c2 because both of these were zeros. And 2 is equal to negative 7 c1 minus 3 c2. Nice. So times 3, we get 3c1 plus 3c2 equals to 6. And negative 7c1 minus 3c2 equals to 2. Add these equations, this dies. We get negative 4c1 equals to 8. c1 equals to negative 2. You guys okay over there? And c2 better be 8. What happened? What happened?
Wait.
I'm waiting.
I got C2 is 4. C2 has to be 4 because that you can't have A plus 2 equal 2. A minus 2 equal 2. It has to be 4 here.
Oh, I looked at this equation instead of looking at this equation. Yeah. C2 needs to be 4, I said. So pay attention. So what do I have now as a particular solution? X of t equals C1, which is negative 2e to the negative 7t, plus 4e to the negative 3t. And that would be particular solution because we used every, right? Cool?
You said
Yes.
when you differentiate the distance.
You get velocity.
Oh, I didn't know that. And you get velocity, and does it work backwards?
You take an integral.
Integral.
So it works
You take the integral of the velocity to the distance.
You go down.
All right.
You go.
So now we're going to dig a little bit deeper into this because they also want to know about frequency and period, which we know we have when we have these trigonometric solutions. So we are looking at free undamped motion. And this means C is equal to 0, undamped, right? Maybe I should underline this, put a little star, and then put a little star over here so you know that that means that. So now, when C is equal to 0, your equation becomes just this. And if you go and say, divide everywhere by m, you get k over m x equal to 0. Now define, and we'll see why, define omega 0 to be square root of k over m. So if you do that, your differential equation becomes, and now plug in, your differential equation becomes this. So now this is our new and improved equation. So we divided everywhere by m, got to the next one, we don't like that k over m, and now we're not going to define k over m equals omega 0. We're going to say omega 0 is equal to square root of k over m, and then we get omega squared over there. Why do we want omega squared? We want omega squared because, remember, characteristic equation, you are going to get r squared. So you're going to get r squared plus omega 0 squared equals to 0, and that one is easy to factor. Right? So now with this characteristic equation, you get your solutions. It's a plus there. So you get r plus omega 0 I, r minus omega 0 I equal to 0. And you see that you have complex conjugate pair. Now that spells x of t equal, there is no real part, so no e, it's just c1, and here is the awesomeness of this omega squared. So c1 cosine omega 0t plus c2 sine omega 0t. If you took physics, you saw this equation. This is the solution. And what is the omega 0? Does anyone remember? It's circular frequency, right? Circular frequency. which is related to the period of the whole thing. Now, we want to combine this into a single equation, and you can actually do this if you use manipulation, which I don't have time to derive now, but it's done in a textbook. It's very easy manipulation. By writing that C is equal to square root of A squared plus B squared, and cosine alpha is A over C, and sine alpha is B over C. And when you apply all of these things, you get x of t is equal to C cosine of omega 0 t minus alpha. Whew. Remember this one from PreCalc?
What page is that?
138. It should take you less than 3 minutes. Now, I said it should take him less than 3 minutes. Well, we all have different different background in proofs. He loves proofs, so he is going to derive it. Now, you know from your PreCalc 2 that this number here is the amplitude.
Yes.
You know that omega 0 is related to the period. Over here is called the circular frequency. And angle alpha, phase angle. So this is the equation that you want to know. Now, you have the period. T. So period T is defined as 2 pi divided by omega 0. And the frequency ni is equal to 1 over t, which is omega 0 over 2 pi. A whole bunch of homework questions will ask you to find frequency and to find a period. Now, you might say, why is something like this important? Well, if two things are not synchronized, mechanical systems, linking them together would be disastrous. The best example is in electrical engineering. If you have electrical system, electrical grid, which has, you have electrical grid which has 60 hertz oscillation, right? And you want to bring up a generator and hook it up to the grid to put more juice into the system, right? You want to produce more energy and to pump it into the system. You have to synchronize that with the grid. Otherwise, if your incoming signal is not in sync with the signal that it's already in the grid, you create destructive interference of waves, right? And what that does to your generator? Exactly, yes. Makes it into a barbecue, right? So, this stuff is so real, guys. This stuff is so important. If you want to be an electrical engineer, you don't understand this stuff, it's not going to happen for you. This is as the simplest terms that I can tell you. It's not going to happen. because you have to be able to sync the your new incoming signal with the pre-existing signal. Now, that's not just when you're hooking up generators. Pretty much any two waves interfering. You can think of waves of any kind: earthquakes, water waves, sound waves, light, and then electricity, right? They're all waves. They propagate through different medium, but they all have the same equation, the wave equation, right? And it's a wave up there. Now, this is a 2D wave. You obviously have the wave equation in 3D. If you have the ripple, like you toss something into the still water, it's a wave that propagates outward in a 3D sense. So yes, we have partial differential equations for the of the second order for a 2D equation that you solve exclusively through power series. Not the stuff we're going to do here. You take the PDE course for that with the boundary conditions and all of the other things. So this stuff actually builds up. Now, the homework will clearly ask you to find the frequency and the period. So whatever problem you pick, determine the period and the frequency of the simple harmonic motion of the 4 kilogram mass at the end of the spring with a spring constant of 16 Newton meters. Awesome. You have no issues, hopefully, dealing with that. So this is problem number 1. It says determine the period, right, and the frequency of the 4 kilogram object that it's hanging on the 16 Newton per meter spring, right? You immediately know, right, that you defined your omega 0, right, as square root of k over m. So omega 0 is square root of k over m, which is square root of 16 over 4, which is 4. So it's 2, right? And you're done. Newtons per meter. Newtons per meter. So period is 2 pi divided by omega 0, which is 2 pi divided by 2, which is pi. And that would be seconds. So every 3.14 seconds, this thing repeats itself, whatever it is. I don't know what the system, right? Well, we know it's a spring, right? So it takes 3.14 seconds to go all the way up and all the way down, and then all the way up and all the way down. So all of that takes 3.14 seconds. And then the frequency, ni, is going to be 2 divided by 2 pi, which is 1 over pi. Now that is the second to the minus 1, which is hertz. So that's what the hertz, if you now think about a little bit of your processors in computers. If they work on a cycle that is 2 gigahertz. Gigahertz. No. 9. Yeah, 2 to the 9. So 2 gigahertz is 2, 1, 2, 3, 1, 2, 3, 1, 2, 3, second to the minus 1, which is 1 over second. That means 2 billion cycles per second. 2 billion cycles per second. And you know what? Your brain is faster.
What?
Your brain is faster than that.
What's our brain?
Some brains. Your brain.
All of them. All of the brains are faster than this. Uh-huh.
I'm not feeling that.
Oh, I'm going to look up the hertz for a brain.
Yeah. It's going to hurt, yes, when we find
What are
it.
the hertz for a brain calculated?
We will discuss a little bit more of these problems next class, but I hope you will be digging into the homework and working this stuff out. I will see you on Thursday. Oh yeah, should we talk about the exam? We have a minute or no? Yes, talk about the exam. All right, bye, stream.